Okay, in this tutorial we're looking at section 11.3, which is other applications of first order differential equations. Okay, they give us a few different examples of investments and money. Okay, they tell us that dp dt is equal to PR. Okay, but when it comes to our investments and money, okay, we know that it's essentially the same as our growth equation from the section on 11.2. Okay, which is P of t equals P naught e to the RT. But P naught is our initial amount of money or our principal. Okay, R is our interest rate and T is our time. Okay, our pressure and height, dP dH equals negative Kp. Our drug disappearance in the body, okay, is dd dt equals negative Kd. And light intensity and depth is di dx equals negative Ki. Okay, so what we can do is a couple of worked examples on this. So have a look at worked example 4. So when money is invested in a bank at a constant rate of R%, with continuously compounding interest, the accumulated amount in dollars of P at a time t years after the start of the investment satisfies the differential equation of dP dt equals PR. Okay, assuming an initial investment of P0 dollars, okay, for part A, basically what they're asking us to do is come up with this equation. So for part A, there's really not much point doing it. So it's P equals P0 e to the RT. Okay, because we know that. Okay, and we want to determine the amount to which $10,000 will grow in 6 years if invested at 0.45%. Okay, so what we need to do is say, well, our P0 equals $10,000. Okay, our R is equal to 4.5%. Okay, so our P equals 10,000. Okay, E to the our R is 4.5%, which will be 0.045 times our time. Now our time, is actually 6. We know that. Okay, so it's simply a matter of doing a bit of work on our calculator, which gives us $13,099.64. Okay, is what our money would have grown to. Okay, so there's really not too much to work example 4. Have a look at work example 5. Okay, the population of a certain town increases at a rate proportional to the square root of the current population. Okay, in 2000, okay, we had a population of 250,000. Okay, in 2008, okay, we had a population of 640,000. Okay, express the population number n in terms of t, the time in years after 2000. And then we want what the predicted population is in 2016. Okay, well, we can say our dn dt, okay, is k times the square root of n. Okay, and we know that n naught equals our 250,000. Okay, so what we can say then is our dt dn is equal to 1 on k times the square root of n. Okay, so that means that we can say, well, that's 1 on k times n to the power of negative a half. Okay, and what we need to do is integrate this, so we can say that t is the integral of 1 on k n to the negative a half dn. Okay, we can bring our 1 on k out, so t equals 1 on k outside of n to the negative a half dn. We can actually multiply by k as well, so we can say it's k times t equals the integral n to the negative a half dn. Okay, so kt is going to equal 2n to the half plus c, or ket is going to equal 2 times the square root of n plus c. Okay, well, we know that when t equals 0, okay, that our n equals 250. Okay, so what we can do is say, well, we've got, come up here, and say, well, 8k, 2 times the square root of 250,000, okay, plus c. Okay, when we work that out, okay, we find, oh sorry, that would be, sorry, wrong one. That's our 0, sorry, our initial one. Okay, so when we work that out, we find that c equals negative 1000. Okay, so we know then that kt equals 2 root n minus 1000. Okay. So we also know though that when t equals 8, that we get 8k equals 2 times the square root of 640,000, okay, minus 1000. Okay, when we we simplify that, so 8k equals 600, so k equals 75. That means then that our equation becomes 75t equals 2 times the square root of n minus 1000. Okay, what we need to do is keep rearranging this for n of t. Okay, so and say then that our 2 times root n equals 75t plus 1000. Okay, so that means that we get root n equals a half outside of our 75t plus 10,000. Okay, which means n equals a quarter outside of 75t plus 10,000, sorry, plus 1,000 squared, so not 10,000. Okay, so we've got our equation for n of t. When t equals 16, so n equals 1 on 4, so 75 times 16 plus 1,000 squared. We work that out, it's 1,210,000. Okay, so that's what our population would be in the year 2016. Okay, we've got one more worked example to go. Okay, which is worked example 6. This one is a worked example on population models that have a regular removal. So a farmer initially has 200 sheep. The number of sheep on the farm grows at a rate of 10% per year. Each year the farmer sells 15 sheep. Write the differential equation modelling the number of sheep n on the farm after t years. Okay, well we know that we've got a k value of 0.1 because that's our 10%. Okay, so we can say that we've got dn dt is equal to 0.1 times our n minus 15, or you can say that we've got dn dt equals n on 10 minus 15. Okay, or we could say it's n minus 150 on 10. Okay, and we know that our n naught is, sorry, we also cut out that our n naught equals 200, which we'll need in a minute. So we can say that our dt dn, oh no, sorry, that's all that we needed for the first part, sorry. That's part A taken care of. In part B, okay, we need to solve the differential equation to express the number of sheep n on the farm after t years. So this is where we're going to flip it and say, well, our dt dn is equal to 10 over n, sorry, our dt dn, okay, is going to equal 10 over n minus 150. Right, minus our 150, so we're going to integrate that. So t equals the integral of 10 over n minus 150. Okay, dn means t is going to equal 10 log to the base e of the modulus of n minus 150, okay, plus c. Okay, so we need to substitute in our t equals 0, n equals 200, our initial condition. When we do that, okay, we find that we get a value for c of negative 10 log to the base e of 50. Okay, so that means our equation is t equals 10 log to the base e of our n minus 150 minus 10 log to the base e of 50, which we can simplify to t on 10 equals log to the base e of n minus 150 on 50. Okay, so we're getting there. Okay, and then we can do our Liffey method, say that e is t on 10 equals n minus 150 on 50. Okay, so then we're going to have n minus 150 equals 50 e to the t on 10. So n equals 50 e to the t on 10 plus 150. Okay, so that's our part B taken care of. Okay, so we're getting there, and then part C is determine the number of sheep on the farm after 5 years. Okay, so that's just a simple n equals 50 e to the 5 on 10 plus 150. So 50 e to the half plus 150. Okay, we just put that in our calculator, which is 232.44. Okay, which means there would be, we need to round down, okay, because we can't have part of a sheep. So we can say there'd be 232 sheep on the farm. Okay, so look, I think you'll get through these questions without too much troubles or too many difficulties. Okay, have a look at the worked examples when you're doing the questions. I think you'll have not too many dramas with getting through these questions.